as of January 2012. At that time, there were 7,300 people as members of Global Link. So this was not a small little, enterprise. It was a fairly substantial and significant one. And you can see the growth in membership from 92 all the way up until 2012. And we start here with the FCTC coming into play, and we continue to get growth in.
Are these public officials?
These can be anybody. They're primarily academics, advocates, and activists. Okay? Sometimes they'll be government officials, but not primarily.
Tom?
Yes?
Were you successful in keeping out members of the...
Yes. Tobacco industry, yes.
Right.
Yeah. I wasn't. I didn't have anything to do with this.
Right.
Yeah, but the people that were, I wasn't even a member of this.
Hard.
Yeah, so and then last fall we published our first really comprehensive analysis of the diffusion of innovations theory applied to global health, to global tobacco control. What was really interesting is I just realized this last week. I published my book in 1995. I published an updated chapter of the diffusion network data sets in 2005, and then in 2015 I published this new paper that is a fairly comprehensive. So it looks like every 10 years I manage to produce something that's of significance or worse. So hang on. So we wanted to look at what drives treaty ratifications, right? You have country attributes. They might be population, size, tobacco production, income, and then we have a number of different networks. And in this particular analysis, we use 6 networks. Distance, and we recoded it on the median, so if you're close or not to other countries, general trade, tobacco trade, and then 3 networks that we extracted from the Global Link data. The referrals, who are what people from what other countries referred you to be on Global Link, posts to different Global Link messages, and co-subscriptions to the same services. There are 48 services available on Global Link, and if people subscribe to the same services, we created a link between those 2 countries. It's a 2-mode bipartite network. When we do the analyses, our N goes to 754, right? So now we've stretched out the data at the number of countries that we have in the data set times when they adopted the treaty, and you can see that early time periods, there are very significant effects of time, so there's a propensity for people to ratify the treaty early in its diffusion, and it tapers off, right? Then we look at network exposures. Distance, general trade, tobacco trade, referrals, posts, and subscription co-memberships. And here it turns out this is the one network where we saw significant amount of diffusion occurring, cohesion exposure, when other countries that subscribe to the same services you subscribe to ratified the treaty, you were more likely then to ratify the treaty in the next time period. Okay? And here are the graphs. We can have time of adoption on the x-axis, thresholds on the y-axis. Look at the networks over time for the 6. These are the 6 different networks and the final graph. So you get a sense of what the diffusion looks like within those 6 different networks. Okay? And so we'll show you how to do this in R, in netdiffuseR, and what's significant about this example, of course, is that we have static networks, dynamic networks, lots of attributes, and a real important adoption behavior that's happening through this network. Okay?
Yeah, so this is the FCTC run V9 file that you guys have out there. So again, the sort of this data is that we have some attributes, right? But we also have an edge list here in this case. So,
and by the way, we anticipate releasing these data, but we're still in the middle of satisfying the specific aims for the grant, and so can't quite do that yet. And in the data set that we actually have 18 networks that we've compiled. Things like bilateral trade agreements, international monetary fund exchanges between, and all kinds of stuff. So we have a number of different networks.
Can we only use those one at a time in our model, or will you throw the whole 18 networks?
You can put all of them in at the same time if you want. In this case, we put all 6 in. Because we've got enough power. We've got 191 countries, and we have 10 time periods. Yep.
So what you can actually do is like to compute the exposure given so you can create DiffNet objects, all of the same size, same number of vertices, but using the different network attributes and network structures. So you can compute, as Tom showed in the slides, you can compute exposure given a different network each time, and then pull all of them together in a regression analysis or probability model if you want to see. So here we have the attributes. Is on a data set here, which looks something like this. We have an ID, ID numbers, country codes, year, which is important in our case, and many other variables. And the network data frame has 5 variables in this case. So we have an ID nomination. So this is basically ego and outer. And we have the relation, which is the type of network that was created. And we also have a dynamic attribute. So this will allows us to create dynamic graphs.
Right, so we have dynamic network data and dynamic attributes. Country population is changing over time, their tobacco production, their smoking prevalence, all that's changing over time, and we want to incorporate that in the model.
Okay, so and just to show you here, so this is the way, so we wrote this in through all the relations, all the types of networks, and here we are applying the edge list to DiffNet function. So again, we have an edge list, and we have the time 0 so we have an edge list with spells. That's why we have T0 and T1. And then we have the data, which in this case, so the thing is that edge list to DiffNet and survey to DiffNet have a bunch of checks that the function does internally. So if you have some things that do not match, for instance, the number of vertices do not match in the edge list and in the data set, or you have, I don't know, the time span do not match also, the function is going to let you know. And actually it's not going to work. So, but the thing is that we're trying to be like the more explicit as possible when it comes to diagnostics, to tell you whether there's an error or not. So again, so we have the data set here, we have an ID variable, time of adoption, and a time variable, which is dynamic. And here we have a special feature that actually allows you to so if you have more individuals in the edge list than you do in the data set, or vice versa, you can actually ask the function to fill it out so you can work it out later, and you don't worry about it right now.
As a side note, one of the things I loved about this data set is I have 191 countries, and there aren't countries leaving and entering into the world system, although there is a little bit of that. I can safely ignore it.
And we also have so again, I don't know if you took a look at the manual of the package that we sent you guys, but the thing is that we're just showing just a subset of the functions. Right now the package manual has more than 100 pages, 101. But the thing is that so we have a lot of other functions and stuff that we're not showing right now, but so you can take a look. For instance, we have we can compute degree as well as all the pages. I'm just going to run this. So again, you don't have the data of this, but this works for you as an example of how would you use this diffusion. Do you want to see a particular data set?
Let's see, one, in the end, we run it with all 6 exposures in there, right?
Okay, that's fine.
So one of the things we did in this loop, because you're looping through each network, we estimated the model individually for each network, and then we stored all the information that we calculated across the 6 networks, and then at the bottom we run a model that estimates putting all of them in at once. I don't think that one. Was it?
That's the last one.
Yeah, but that's not the regression. Go. This is it.
Is it?
Yeah, because it's got the 6 different cohesion exposures in it. running the model on adoption. All right, so now you can see here are our results. We have our time dummies as usual. They don't turn out to be significant here. We put in a variable for which region they come from, and you can see that relative to Southeast Asia, we have positive effects of being in Africa, in the Americas, or in Europe in terms of time of adoption. Democracy levels significantly associated with ratification. None of the degree variables, so whether or not you're connected in the network doesn't seem to matter, but we do get effects for cohesion exposure to the third network, which is tobacco trade, and to the 14th network, which in our case is this co-subscription network. So if you're co-subscribing, if your countries that you have tobacco trade with ratify, you're more likely to ratify, and countries that you are sharing subscriptions with on Global Link ratify, you're more likely to ratify, okay? And so what this tells us is there's an effect. Being on the Global Link service is positively associated with accelerating the diffusion of this treaty and getting it ratified by more and more countries.
What's the size of the effect for us in terms of the global effect?
The size of the effect is, well, let's see. In the other analyses, we did the odds ratio, it was 4.0, so it was pretty substantial, actually. Pretty substantial. Okay? Were there any other diagnostics that we ran on this that we wanted to show? The main thing was the dynamic attributes, the dynamic networks, and multiple networks. I don't think so, no. Okay. All right. Okay, and then the last case that we want to share with you is a study that is more typical of the kind of behavior change study that we do in the social sciences, where you have data at 1 or 2, maybe 3 or 4 points in time. And this particular study was a study of testing different network boundaries and peer influences on substance use, okay? And we published this in Social Networks in 2013. We had a survey that we were able to develop, which is the best survey I have ever constructed, simply because it was allowed to be a network survey, right? Most of the time when we do research, we've got a survey about X, and we're allowed to add some network questions later on. But in this case, we had a grant to study social network influences on tobacco and alcohol use. So we start out collecting network data, egocentric network data, and then we asked students to tell us the first and last names of their closest friends, write down the roster ID number, because we gave them a roster with the pictures of all the kids in their grade with ID numbers underneath them. They love that. They love looking at their pictures and looking at their friends' pictures. So they write the ID numbers down, we ask a few questions about those friends, and then we ask other network questions. So not only who are your friends, who do you admire, who do you think is successful, who do you want to have a romantic relationship with, which I think is particularly interesting, and who are the most popular. And where did I come up with these network questions? Was it theory? No. I thought about my high school yearbook, right? People get voted as the most popular, people get voted as the most likely to succeed. So I figured those are relationships that adolescents would be familiar with, and it seemed to work pretty well. So these are California schools, so they're large. There's 5 of them. There's a few hundred kids in each grade. This is just one network diagram of one of the grades. We dropped the isolates from the graph. Okay, and so now we're going to run the SNS code. So this is a panel data set. We interviewed the students in the fall of their 10th grade year when they were 15 years old, in the spring of their 10th grade year, so it's within the year, and then the spring of their 11th grade year and the spring of their 12th grade year. Okay, so we actually have 4 waves of data on these students with the same ID numbers over time. And what we want to know, of course, is are exposures associated with starting to smoke between one time period and the other. And in this analysis, we're only going to look at the first time period and the fourth time period. Okay? So we're going to look at a 2.5-year window from when they started high school and when they near finished it. All right, so we have, again, it's a DiffNet object, survey to DiffNet. We have a photo ID. We have a list of the variable names that are the network variables. So here before, notice we were putting in the actual names in quotation marks. Net11, Net12, Net13. Here we've created a list of those names and we just enter them there. And we have our time of adoption variable, and in this case, the time of adoption when the person started smoking. It makes a DiffNet object rather quickly, DiffNet smoke friends. Right? You've already run that. And then we created a separate DiffNet object for the drinking behavior, DiffNet drink friends. And now notice here, we're just looking at the friendship network. We have the other networks loaded, we can pull them in, but right here, we're just going to look at the friendship network. In fact, the results of our paper that we published in 2013 showed that if influence occurs, it's most likely to occur in the friendship network rather than the other networks.
There's a friends drink network. So we have the friendship network and the time of adoption is for drinking.
Do you have the smoking one too?
Yeah.
Yeah, okay. Right, so again, you can look at your DiffNet object, and it tells you the number of nodes, 2164, right? Their ID numbers, the time periods, 2010 to 2013. It's a directed graph. The final prevalence is 42%. So that's the smoking rate at the end in 10th grade, in 12th grade.
42%.
Yeah, it's high. And then a whole bunch of dynamic attributes.
Yeah, so by the way, the smoking variable here was built as asking them whether they ever have ever smoked or not. So that's
Yeah, so
like
these
they're
are
active
people that may
smokers.
have just tried once.
Yeah,
and-
yeah,
Yeah.
yeah.
But the reason I work with that variable a lot is tobacco is so addictive, it is really hard to quit. And kids who just try it a couple times can oftentimes become smokers. And now with e-cigarettes, we've got a lot of kids starting with e-cigarettes and transitioning to regular tobacco use.
Yes, we were just assessing the one variable of the different object schools, and since it's dynamic, we get just the first element. So now it's a vector. Exposures.
Yeah, so now we're going to calculate exposure. And we calculate exposure with this one simple, this is amazing. With this one command, we are calculating exposure at all 4 waves of data. And here we're calculating contemporaneous exposure.
And for the keyword, this is another example. So keyword continuous exposure, but this time is weighted by degree. So this is attribute weighted. So
Oh, right, so this is really cool, right?
So
And we think this is important because in a school-based context, if popular kids are smoking, they're going to have a stronger influence on the smoking behavior of their peers than just regular kids who are smoking, right? So we can create a degree-weighted exposure variable. And then we can calculate exposure for drinking.
So would you still say it's adoption if they've tried smoking? I mean, isn't that random exposure? I mean, if you tried smoking, if you had a friend, you tried smoking. I mean, whether that's
Is it
adopting
adoption?
behavior.
Oh, if you only tried it once and then
Yeah,
quit.
that could just be exposure.
Yeah.
you know?
Yeah, that's, no, right. They could have been exposed, tried it once, but then decided they didn't want to continue, and they stopped. Yeah, so, and we can work out those nuances in the data if we wanted to, for sure. And a lot of times we do this by creating a variable which is non-smoker, non-susceptible, susceptible to smoking, which means that they responded to a particular question in a particular way. They refused to say that they would never smoke in the future. So that's susceptibility. Then if they've ever tried a cigarette, so experimental smoking, casual smoking, regular smoking.
Okay.
So we could create that kind of variable where it's scaled.
Yeah, and the following line, we just build the data frame to work with. So, for example, here this is different from the other examples in the sense that we're not including the option that's as data frame. So, when we don't include that option, what we end up getting is actually a list for the length of time period. So, we can access each slide by the same way that you would in a list. So, I'm accessing slide number 4 here, number 1, and then since within each slide you have a data frame, you can access the variable as well. So I'm accessing the variable TJ01 in slide 4.
So this is important because we've taken our diffnet attribute, we're putting it into a data, it's not a data frame?
It's a list.
It's a list. It's a list. So now, and that list is indexed by the time period, right? We have 4 time periods. So we can access all the different objects in each one of the lists by going to the time period and pulling out the variables that we're interested in, putting them into a data set. And then we did it separately for both smoking and drinking. And you know, the thing is, to do this in a statistical package would take forever, you know, and R is just very, very efficient at doing things like this, okay? All right, now we're going to estimate the model, or your smoker at time 4 as a function of the school, your age, being female, whether or not you're getting a free lunch, SES variable, your academic performance, your health status, the number of rooms in your household, parental smoking, sibling smoking, whether or not you were a smoker at 10th grade at time 1, and then if you were a drinker at time 4, and you know, we're just getting the p-values here, aren't we? Okay, and then, I know why, because we're getting the coefficients up here, okay. And then cohesion, exposure to smoking at time 1 is not significant, but exposure to smoking at time 4, contemporaneous smoking, is associated with becoming a smoker. Remember, because we've entered smoking at time 1 in the model, this is becoming a smoker at time 4. People who became a smoker at time 4 were more likely to have smoking friends at time 4. Make sense? And it's a very strong coefficient, right? Questions about that? So this is to illustrate what it's like when you have a regular kind of panel data set. And again, we can do an awful lot with really not that many lines of code when you think about it. And then we estimated the drinking model as well, and we didn't find an effect on exposure to drinking, which surprised me.
Why do you think that is?
I don't know. I don't know. I have to think about that because I'm puzzled by that. Yeah. Did you run the drinking model?
Yeah, this is the drinking model.
This is the drinking model.
Yeah.
Yeah, so we don't get a cohesion. Oh, but that's degree-weighted exposure. But we did it with the regular exposure too, and we didn't get an effect.
Is there a parent and sibling drinking variable?
There is, and they need to be in that model. Yeah. And drinking behavior is even more prevalent. You know, maybe that because it's so prevalent gets washed out. I don't know.
Quick question.
Yes.
Just about, in general, those statistical procedures you've done for a lot of the GLMs, things like that.
Mm-hmm.
Of course, that's ignoring a lot of the dependencies.
Right.
I'm wondering, I'm having a hard time remembering, but I thought I saw in that manual that you had functions that would implement things like QAP, something like that would be more appropriate.
Do we have QAP? I don't think
I
we've
may
implemented.
be misremembering.
Yeah. We haven't implemented a QAP. We are.
Or, I mean, something.
Yeah, right. No.
We do have an non-parametric test that we are developing. Right?
Yes.
But this is new theory, and we want to show it to you actually. So
Yeah, yeah.
It-
But we're very conscious, at least I am, that, you know, ergoms and Sienna have been developed to take care of that dependencies. And the statistical approach we're doing is by and large ignoring that. And I have always felt like, in part, you have to do both. This kind of framework is very flexible for testing a lot of things out for theory. What it ignores is the tendency for reciprocity. The two that I'm mostly concerned about are reciprocity, transitivity, and homophily, which are there, and if you don't control for them, maybe, you know, the effects that we're seeing are actually not there because we've masked those other things and ignored them. I'm conscious of that. At the same time, I also realize we've been working for, what, a year, 2 years, trying to estimate Sienna models on these data. And we can't get them to converge, we can't get them to work. And it's not like we haven't been working with Tom Snyder to do it. So when you get into these kinds of things, they're really challenging. And I feel like we can move forward theoretically using this framework, understanding that we have that limitation. And in fact, in the paper that we published on this data, just looking at the baseline data, we ran ergoms on 300 networks. So within this baseline data set, we have the 5 networks for egocentric, anywhere, and then we're able to pull out from that the people that were in their grade. 5 networks in your classroom, 5 networks in your grade. And when you add all those up, we had something like 400 networks. And so we estimated a common ergom on smoking and alcohol across all 400 of those networks, then aggregated the coefficients to determine in which cases, which network and which boundary conditions were most likely to be associated with homophily on the behavior, controlling for structural effects as well as homophily effects. So we did that, and that was a big undertaking. But now to do that longitudinally, that's another order of magnitude challenge. That we, you know, we have another year in the grant to solve. But that's a great comment, and in some ways, I think one of the exciting things that's happening in our field right now is balancing these kinds of approaches and making sure we're taking care of dependencies that we need to take care of, but not throwing the baby out with the bathwater. Because we've also done some work with small kids networks, and once you control for those structural effects, you lose the homophily on the behavior. But on the other hand, we don't know which comes first, you know, homophily on the behavior versus that. So obviously we need good longitudinal data to sort that out. Yep.
And also, I don't know, but while we're discussing in class, there's not like an actual sensitivity of how big are all these problems actually in the real data. So when you run this kind of model, so how big is the issue that you have dependencies between individuals?
Right, right.
We actually don't know, and we're not sure.
We're not entirely clear on that, yeah. Okay, so we just have this slide in here to emphasize, are we finished with SNS? I think so,
Yeah.
for now. Just, you know, to let you know, these are, to me, what a lot of the features that we have now in netdiffuseR. You can calculate thresholds, indirect exposures, attribute-weighted exposures, network-weighted exposures, infectiousness, susceptibility, and we also have something called an ego-alter table, which I'll show you. And this is built into the software. We haven't really used it yet, but if you have behavior at time 1 and time 2, for each ego, they can be a yes or a no on each outcome, and each alter can be a yes or a no on each outcome at baseline and then at follow-up. And it actually gives you 16 different possible scenarios in terms of the egos and the alters, and I labeled all of them, whether or not you have constant homophily, alter-created heterophily, simultaneous, you know, all these different things. And so we haven't done any work on that theoretically, but I think it'd be really interesting if you have, you know, behavior change over a couple time periods. You can look and see what proportion of these different cells do you get over time, and what are the characteristics of egos, alters, and relationships that lead you to fall into these 16 buckets. Right? Okay, good. So that's that.
You're missing one part.
You are missing one part.
Yeah, and
Which one do you want? We got to to the end of this.
No,
Oh, we didn't, that's right, that's right.
no, we.
The bonus track, yes.
we-
So this,
Yeah, so,
first purchasers, you know, this is an incentive, we give you a bonus track. Okay, this is George.
yeah, so just a quick look on this. So this is how we actually compute structural equivalence. This is well documented on the package, so you can take a look. I'm not going to explain it, but I think it's pretty well explained on the package with the appropriate references for doing so. That's why I sent you the manual, because in the manual you can see the formulas nicely done. So seeing this formula in plain our code is not nice, but with the package it shows nice, so you can see there. Here's how you compute structural equivalence, so you can actually get structural equivalence only instead of just computing exposure structural equivalence. You can compute just the structural equivalence like this. Exposure is implemented this way, so you have a network here, which could be structural equivalence or the actual graph. Some attribute, which in some examples has been degree, and the adoption matrix. And this is how you compute it. And what I'm showing here is that what you gain when you use attribute-weighted exposure instead of just plain exposure. So you actually gain more variability in the data. So as you see here, the plain exposure gives you threshold levels like this. But when you include, for example, in this case, professional age in the medical simulation data, you get more heterogeneity in the data, which is good for estimation purposes. This is infectiousness and susceptibility. You can check the math later if you want. This is a nice plotting that you can get. In this case, you don't get much, but if you have a big graph, lots of nodes and vertices, you can actually see some really neat curves.
We should give a shout out too. This was inspired by Sinan Awal's work, who first published this kind of heat map of infectiousness and susceptibility in his science paper.
Yeah, and you can do it with one line here.
Yeah.
So you have your network. You can set the number of time periods that you want to include in the infectiousness and susceptibility graph, and whether you want in large scale or not. And with infectiousness and susceptibility, you can also. This is an example of what can you do with this. So here we're just running some t-tests to see if it's different from zero, infectiousness and susceptibility. The bonus track. This is what we were just discussing. So we have a work in progress method that is a structural dependence test. That's how we call it, which basically tests whether, like in simple words, whether some covariate is associated with a network. So for example, when we talk about times of adoption, we say that if there's the threshold model fits, we say that the times of adoption are a function as well of the network structure. So you will adopt earlier or later, depending on how well we are connecting the network. And this test, we believe, allows you to test for this kind of stuff. So this is the setup. We have a work in progress paper, so if any one of you wants it, we can distribute it as well. So basically what we are saying here is that, so given a vertex attribute, for example, times of adoption, like this here, and some statistic which in this case is threshold, which is based in times of adoption and the network structure as well, that's why it's like this. We say that if the attribute and the graph are like independent, we get that the expected value of the average statistic it's equal to the expected value of the semi-statistic without being dependent on the graph structure. So it's kind of hard to digest at first, but we can check it out like this. So what we basically do is like we take the baseline graph and we run simulations. In these simulations, what we do is that we rewire the graph. In order to we preserve the degree of each vertex in the graph, and after we do that, we recalculate the statistics. So in this case, we have our network, which is a simulated network, and each time for each rewiring that we actually run 1,000 times, we recalculate the average threshold, right? And after we do that, and the thing is that in this network in particular, we know that the threshold model fits because we simulated the network using thresholds, right? So we know that like network and threshold levels are together, go together. So in this case, what we get from the output is that we say that the probability of that the network, okay, the probability of having this, in other words, that the threshold levels are not joining with the network, it's close to 0, so it's highly improbable. That's what we're saying here. So, and if we see, we can plot histograms using the hist function that contains it. So, in other words, so when we computed the threshold, the average threshold for this network, the original network, we got a value around here. And once we rewire it and retrieve the empirical distribution function of the average threshold for the rewired graphs, we get this distribution, which is very far away from the original one. So here we are saying that threshold levels are actually like go with the diffusion model, right? And how can we test this? So in the following example, we have the original network, but now I'm changing the times of adoption. So some random vector actually. So now I know that actually the threshold levels and the network don't go together. It's just the times of adoption do not depend on the network structure. And as you can see here, I'm changing the times of adoption on the definite object using this function. Again, running the same test, we get a different result, right? So now we see that actually the threshold levels that we observe are not together, to say it somehow, with the times of adoption variable. So this is a way to test whether threshold levels like the diffusion model goes with this network. And the nice thing of this test is that it's not parametric. It's not based on any assumptions on the distributions. And since you are randomizing, simulating the networks, keeping the structure of the network, all of these are comparable between each other. Does it make sense?
You preserve the degree of the nodes.
Yes.
Yeah. So this is our attempt to build a structural test that that specifically addresses the dependency and tries to test whether or not our variable that we extract from the diffusion network is independent of the network structure or not.
I mean, you could even extend this to transitivity as well.
Right.
In a plot framework where you...
Right. And one of the things that we're kind of now talking about is, well, what about other attributes? Are there ways that we can build in attributes of individuals with some of our tests and infectiousness and susceptibility and that sort of thing?
So formally, we have a proof for this in the case of threshold. We haven't proved it for other cases, but threshold levels, we have shown that the results follow. And actually, there's a pretty nice result. I don't know if it is nice. The thing is that if the network structure is independent from if the variable, in this case, at time of adoption is independent from the network structure, you get that the average expected threshold level will always be 0.5, regardless of the distribution that you have for the thresholds. So you can have a uniform distributed threshold, you can have a normally distributed whatever, and you always theoretically will expect to get a 0.5 average threshold for the network. Which is a problem too, because if the threshold levels are actually depend on the network structure, and it's 0.5, the average, the test is going to tell you that it's not dependent. But we're working on it. It's pretty new.
Yes.
Question just on the slides, the previous one. I just find it odd that you may just be misunderstanding what you're doing here, but I find it odd that you're just randomly, uniformly, from 1 to 20, choosing the time of adoption rather than just a random permutation, essentially using the empirical distribution.
So this example is just to illustrate when does the test shows you that the data actually does the variable, the underlying variable does not depend on the network structure.
Oh, I see. Okay.
Right, so this, right, it's not part of the test. This is an illustration that if you had a random type of adoption, the test would fail.
Yeah, yeah, but that's Does this make sense?
Yeah.
So that is what we are trying to test here. So in the first example, we got that the p-values are close to 0, right? Because it depends though. So the attribute depends on the network structure. But in this case, we know by construction that the attribute does not depend on the network structure. And that's why we accept this, the null hypothesis that we see non-structural determinants.
So we'll keep you posted.
Yeah.
So we have some time, I think that's everything, right? We have some time, as we look at that, we stayed right on track. We're incredible.
Yes.
And so we have, 10 minutes for questions, requests, feedback. Yes?
I'd love to hear your thoughts about another sort of country diffusion model. We don't have this website of people interacting. Are there other ways to think about constructing a network between?
There are, as I mentioned briefly, we have 18 networks in this data set. So trade was one that came up, and trade changes every year, so that's really good. And we had tobacco trade. Bilateral agreements, there are all kinds of agreements that countries are making with one another and negotiations that they're carrying on with one another. We had originally a bunch of telecommunications traffic data. I don't know if any of you know George Barnett, but he's been compiling telecommunications traffic between countries for a long time. And that data was really good for the first couple of years, but then with the internet, it all changed. Now you no longer had phone data that used to be available. So that communication traffic data kind of fell apart on us, which was one of our original hypotheses. I'm trying to think what other sources of data did we get? Those are the ones.
But who adopts these tobacco control?
Treaties?
Yeah.
The governments do.
It's the government.
Yes.
But it's probably some kind of health agency within the government that's driving the.
Possibly. There's a lot of variabilities, and I think you have a question: are the processes that countries go through to make an adoption decision the same as what an individual goes through? And I don't think that's the case. I think there are different processes there. And we searched hundreds and hundreds of attribute variables we tried to build into the model. And one of them that does pop up is democracy and female labor force participation. But I don't know that we capture all the nuances of what that adoption process is. And in some countries, most of the time, you have a legislative branch that has to ratify the treaty, right? But that's not always the case. In other countries, there are different models for the way legislation gets enacted.
But the academic and advocate interactions underneath these countries are driving federal adoption
Yes.
of these policies.
Yes.
That is kind of interesting in and of itself.
That's right.
Not just the-
That's right. The other thing that we have in these data are two other treaties that diffused internationally over the same time interval, one on pollution and one on corruption. And so the ultimate goal was to compare these different, because you can't run an experiment at a global level, what I wanted to do was compare different networks with different outcomes. So I'm trying to find corruption networks that should be associated with the corruption outcome, but not the tobacco one, and tobacco networks with the tobacco outcome and not the corruption. And I was initially running those kinds of models, but everything got so complicated in the R code, and it was now, 40 pages long, and that's when we said, wait a second, we need to build a better mousetrap to do this. And so eventually we'll compare the 3 different treaties across the 18 networks.
But the only network that mattered was the global.
In us, the global co-subscription, the only one that mattered was that, for the tobacco.
Yeah.
But that's the ultimate objective. And I'm certain I'd really be interested in people's suggestions about other sources of international exchange data. We've looked,
I mean, maybe professional interactions from whatever kinds of sort of co-authorship between medical professionals or whatever. I mean, I would think that interactions across borders at the level of professions would matter.
Yeah, quite possibly. Yeah. Now, one of the things that we always have to take into account here is there are 2 countries that have not ratified the FCTC and, in fact, never ratify international treaties. They are the United States, right? Because we think that we're different, and Switzerland. And a lot of these networks, particularly for the US is always central in the network. So sometimes we include them in the network, but then don't include them in the statistical analysis. So the US is a pain when it comes to doing stuff. If you call our Congress a Congress, yeah. It's a group of people that get together in a big white building. Other questions, suggestions, feedback? I felt like our presentation was a little choppy because it's the first time we've done that, so I think we need to smooth that out a little bit, maybe put it all into one document. But we'll be able to fix that.
Yeah, so by the way, so Tom and Stephanie and Tim started developing this like a year ago.
Probably 2 years ago,
Yeah.
yeah, at least.
And I started coding all this like 6 months.
Yeah, October 10th or something, yeah.
Yeah,
so
yeah. So
We're only 6 months into development, which is really incredible.
Good job.
Yeah, good job. Yeah, it really is, it's really incredible. And as I say, some of these functions you would want to use, not even in netdiffuseR, but just simply for data manipulation and tracking, you know?
which is the idea because we don't expect to replace aircoms and that kind of stuff. This is just a companion.
Yeah, it's a different model. But one of the things I think that's kept diffusion network research from progressing is the data management challenges, because the data are so different than we get otherwise. And honestly, one of the things that we want to start doing next is looking at social media data. Because, you know, Twitter, all that stuff, you know, there's a diffusion process going on there, and we haven't quite figured out how to marry the diffusion processes that take place on social media to this classic network diffusion framework, right? In the classic network diffusion framework, you have network data and you have a trace of when people adopt, and you put those two things together. With social media, you have the network and the adoption together. They're conjoined. And so it's a different way of sort of looking at it. And we've talked about some possibilities, but we really don't have a good perch yet on how to solve that problem. So we're willing to take suggestions about that as well.
Yeah, because it's not like just take any Twitter data and plug it in.
Yeah.
You know, it doesn't work.
That doesn't work. Yeah.
So, I must admit that I'm quite new to the fusion literature and things like that. I'm just curious as to whether there's anything done maybe in this package or otherwise that sort of does some simultaneous modeling of both the adoption process and if that adoption can end, say, smoking example, some quitting. There's something like
So there
this
are
adoption.
data sets there
Yeah.
with disadoption, but everything that we've done here incorporates disadoption easily. With the exception of the way we structure the data, we get rid of all the post-adoption cases. If we have disadoption, we have to reformulate that.
Yeah, most of the functions use as input a graph and an adoption matrix, a cumulative adoption matrix.
Right,
So
right.
you can basically put adoption and disadoption in that matrix. Because usually the cumulative adoption matrix is a matrix that is n by t. So it actually marks 1 in each row, starting the point that the individual adopted. So that's the input of most of the functions. So if you have these adoptions, you can like truncate that and put in between zeros and that kind of stuff. I don't know if you follow.
Oh, sure. I'm just thinking there could be some complicated interactions with the method as well. That is some of their alters, the alters start putting with it too.
But that's all built into the functionality. That'll automatically be calculated. Yeah, that is not a problem. We just don't have many cases where we have data like that. And you look at the classic data sets, you know, they collect the adoption at one point in time, so it's all retrospective. But hopefully we'll get data, and I think, you know, eventually with some of these social media and online systems, we'll get data of that nature.
So you have a question when you ask them about whether how often they smoke or drink.
Right, so we can do that with, yeah, we can do that, because there is some quitting, although not very much.
Yeah.
Yeah. Good, good. Yeah. That's a really good suggestion.
Any other questions?
With the weighted networks, what do you do with the exposure? How does that work with trade?
Oh,
$1 billion versus-
no. What do we do about weighting?
You can use them actually straightforwardly. So actually, adoption that's valuable or not.
Right,
And actually, we use weighted networks when we use structured
Structured
networks,
equivalence.
because that's the only way that's useful is as a value network, right? Because otherwise you have a bunch of ones all around and it's not very
Yeah.
meaningful.
yeah, so value data are not a problem.
What's the exposure look like? Like, you know, if I trade 10 versus 1,000, and you have the behavior, and the other one also has the behavior, is that exposure?
So then you have that problem, is, you know, you kind of, you may be comparing apples and oranges, right? Because a 20 for you may represent one person with a high value adopting, and a 20 for me could represent 5 people with low values adopting, right?
Yeah, just a row normalized then for the exposure?
But then once you do that,
So
yeah,
you can either normalize it like before, normalize
actually, yeah.
data. So you always get between 0 and 1. But you can also set whether it's value or not. By default, we actually set it as not value, but you can change that.
the other thing, actually, your question made me think about the other thing that we want to start figuring out is what happens if you have multiple outcomes. And I'm thinking specifically in the diffusion case, you have awareness and then adoption, right? So you have 2 different things that happen. And I think we can build that in, but we haven't created an example for that. Because that's in the survival model, that's there.
Right, right.
Yeah. Yeah. But that's something that we should think a little bit more about. Other suggestions? Obviously, we'd love to hear from you. You have our email addresses. We'll probably push some more stuff out to you to just make sure we've closed the loop and given you everything that's updated. But please feel free to send us messages and requests and suggestions, because complaints, yes. We'll take it all. Well, thank you all for coming this morning. This is great. Our first time. Excellent.
Once the conversation's out, I think it's going to be easy. Maybe, yeah, it's always a good idea to update R and maybe I'll update. Yeah.
So when you put up the next version.
Yeah, how are you? It's so good to see you. I'm glad you all can make it. Yeah, that's really exciting.
Yeah, so it is
Yeah, that's great. Great to take it easy.
It's like the latest version, right? Because for instance, for example, the version that is in Cran right now doesn't have the function survey.
So will you update?
I will include a function. Yeah, and once I update the Cran versions, I will let you guys use it.
Excellent. Yeah. That's great. Right. Right. That would work. That would work perfectly. Yes, because then you have the network and then the behavior. Yep. That's perfect. That would be great. Yeah, I think it's very good. Yeah. Right. Yes.
Oh, so what people say is persistent with the threshold. Yes. So unfortunately, there is some
Right.
When the first time what I did is I started by computing the threshold for the basement ground.
Right.
By construction, depending on the structure of the ground. But then in the simulation.
That's a great topic. Yeah.
Average
The first one I
threshold.
know, I set on the message directory, and then it just creates a weeks later.
Yeah, in that case, because if you see when you rewire the graph, the average threshold is completely different from the basement graph because it's
Lindsay, can you come here for a second?
Yeah, that's what
Lindsay, she's in Communication University of Utah and does message design and is now talking about
so
doing
the
message
threshold is a
design.
function of time of adoption.
Which is exactly what.
Yeah. and
Sorry.
That's why when the second example when it was
I was not.
random times for now
Yeah, it's fine. I don't know if
after when I computed.
Yes, yes. We were comfortable, yep. Okay, no, we're good, we're finished. I don't know who else is. Yeah.
But then when I got there, that's kind of like vacation, like, then there's, I mean, I was studying like more of environmental dynamics, and like, I didn't like the networks. It's fine, it really wasn't like. I don't think anybody's.
Oh, so when I was discussing
And the part
with
has
the virus stuff.
Car, hi, how are you? Good. You get ready to do a workshop?
Yeah, I was like, no one.
How did you everything do?
I think we did very well. We managed our time about what we thought, so that was we were a little rocky in our transition. Just because, George was still doing things last night. We had different PowerPoint files in our markup.
Yeah. But anyway,
But it didn't make sense that if you change.
But it's cool for the first time. It's really
I
nice.
didn't work with.
Let's see, are you using your own?
Yeah. So it's.
And we have to bring a second screen for
I
this,
think they
so we can run slides on one and
Are they gonna leave it here?
Yeah,
Okay.
we can.
Right now, actually,
George thought of it last week, I can bring in a projector. What time do y'all start? 1:30?
I saw Becca last night.
Oh, good. Yeah, she's freaked out, and she's been so busy.
Yeah, she looked like she was just right by.
Yeah, and today she worked the registration desk, and then she went up to LA to take cake riding, and then she had some meetings for the day. And actually Thomas didn't come down with us, he decided to spend the night with his friends last night. So she's gotta get him.
So they're, all three of them are coming down
Tonight. Yeah. Oh, good. Great. Yeah, Kate's been working on that. We've had her, good to see you. You too. Yep. We had her stuffing packets last night, she was working the registration desk.
Oh, she went back and back.
Yeah, she took over.
So I'm working with like, just can message these guys.
I don't know. Tomorrow morning. Yeah. I don't know.
But that's
I'd like to look at this, you all do, because our next class is gonna be on graphing.
Yeah.
So,
you, but I,
I'm not sure if
I have a thought how the
I don't know.
that's like, if I gave two.
Yeah.
Yeah.
Two different types of messages.
I finally sat down to do
almost
your template block schedule.
Oh, highlight on the program, yeah. Yeah, again, I want to make sure where I'm supposed to be, when I'm supposed to be. Hello, Katya, how are you? Good to see you. Yeah, no, I understand. Yeah, it's really cool. We've got a package. But I think we streamed it online. Yeah. Yeah.
Yeah.
And two screens.
spoke
very
two
good.
different
Yeah, it's funny
people.
because George had told me last week, he said, boy, it'd be great to do two, you know, have one doing slides and the other doing the R stuff. I'll get a projector for work. And then last night, you know, about 9 o'clock at night, I goes, wait a second, we got a projector, but we don't have a screen. And he was just gonna show it on the wall. So I actually, Becca asked me if he could bring something. It's great. Yeah, right? Yeah. Yeah, yeah. Yeah, so we solved it for you. You're welcome.
Like
I definitely will have something more.
Yeah, of course, like something very happy.
So in the beginning, it's like.
They're going to use,
Maybe the back,
I grabbed it this morning, I had.
in the beginning.
I just hear the same, my wall.
I feel like.
I mean,
Yeah, you do have to do it, yeah.
I just need some water.
Oh, yeah, they have, yeah.
There's a Facebook group
Yes.
where they can use that as a
Yeah.
communication platform.
very cool.
And so it's something.
Okay, I'm gonna go with that. I'll catch up with you later on. You're gonna get around to it.
What they
Good.
post on.
well, so, see, yeah.
So they code those messages for certain, like, classify them in some ways, and then see like whether, I mean, we see some kind of like message if I can, that doesn't mean adoption.
Isn't that amazing?
Yeah, no, I'm so glad that there's some
Oh, yeah.
messages, please.
Yeah, yeah. Yes, yes. It is a network, yes. Yeah.
Yeah, so are there like
So.
Works that I can.
You, you turn that off?
that's the thing,
I was gonna say,
stuff like
since
with
you're
like
gonna do the
diffusion
introduction,
and messages
that's set up,
and,
might as well take
you know,
the
and
central.